Okay, welcome to the second lecture on multivariable calculus. In this lecture, I'm going to talk more about the geometry of Rn, and we're going to cover in particular some special geometry in dimensions 2 and 3. In dimensions 2 and 3, there's a special binary operation called the cross product. This doesn't exist in dimensions 1 or dimensions 4, 5, 6, and 7, and so on. But it does exist in dimensions 2 and 3, and so we're going to define it and explore its properties. In particular, we're going to learn how to compute the equation of a plane and the distance of a point to a given plane. All right, so let's talk about the last lecture. You remember in the last lecture, we learned how to use the dot product to compute the projection P of a vector y along another vector x. So it looks like this picture. And the formula is given by this. P is x dot y divided by length of x squared times x. And the angle between the two vectors is the inverse cosine of x dot y divided by the length of x times the length of y. So you can compute the angle and the projection purely using the dot product. But I want to return to another kind of geometric question, which is how do you compute the area of the parallelogram spanned by two vectors like this? So the area would correspond to this blue region. Now, we have a formula for the area. The area is just length of x times the length of y times the absolute value of sine theta. We know that just from trigonometry, because this vector here in this picture, the length of it is the length of x times the length of y times sine of this angle, whereas the length of this p would be cosine. All right, well, that's one formula. And because I can compute this theta, you would think we have a nice formula for that. But let's try to find an even nicer formula. All right, so let me redraw the picture up here. So we have a vector x, we have a vector y, and I want to compute the area of this parallelogram. And I have an angle theta, and I know that the area, this is p, this is y minus p. We know that the area of the parallelogram equals base times height. And that is equal to the length of this vector y minus p times the length of x. Okay. One thing you'll notice is that y minus p is perpendicular to x. You see x is in this direction, so this is a right angle, kind of by definition of p. And so these things are orthogonal. So a nice trick would be to take x and to kind of rotate it by 90 degrees counterclockwise until it points in this direction. Okay, I try to give it the same length. I'm going to call this vector x perp, x superscript perp. Okay, and now x perp and y minus p point in the same direction. Okay, so this is equal to y minus p dot x perp. Okay, because the dot product equals the product of the lengths when they point in the same direction. That's kind of a consequence, if you want, of this. If the angle between them is 0, then this number here has to be 1. And so those two, the numerator and denominator, are equal. So in other words, in the Cauchy-Schwarz inequality, you have equality when the two vectors point in the same direction. Okay, now I got to be a little careful here, because the fact that they really point in the same direction and not in opposite directions is a consequence of the way that I drew the picture. So if I had, drawn x kind of to the left of y, then they would be pointing in opposite directions. So I should be a little careful here, and let me put absolute values here so that it still holds true even if they point in the opposite direction. So it's not a manifestation of just the way that I drew the picture. Okay, well, let's try to compute this. So like I said, this is now the dot product, but x perp and p are perpendicular. You see from the picture, here's P, here's X perp. That's kind of by definition because X perp is perpendicular to X, and P and X point in the same direction. So the contribution to the dot product of this P dotted into that is 0. And so in fact, I just have absolute value of Y dot X perp. Okay. Now, one more observation is that I can write X perp very easily. So I'm going to pretend now that I'm in 2 dimensions. Okay, so this is all for dimension 2. We'll do 3 dimensions later. But if I'm in dimension 2, there's a really easy way to write X perp. Okay, so let's see that. If X is X1, X2, then X perp is just minus X2, X1. Those are its coordinates. Okay, why is that? Well, you can just inspect it. If you take these 2 vectors and you take their dot product, you're going to get minus X1, X2 plus X1, X2. So their dot product is 0, so they're perpendicular. That's good. And also the length of X perp is the same as the length of X. Why is that? Well, because if you take their length, you square the entries and take the square root, and you end up getting the same thing because I get X1 squared plus X2 squared and then the square root. And here I get X2 squared plus X1 squared and then the square root. So they have the same length and they're perpendicular. And okay, I could have put the minus sign here and the plus sign here, and that would have corresponded to a rotation in the other direction. So you can check that if you put the minus sign here, then it corresponds to a counterclockwise rotation, because if X was pointing in the, in the X direction, then now it would be pointing in the Y direction. So if this was 1, this would have to be 1. So, okay, so this is a nice formula, and that allows us to continue our calculation from up here and see that this is equal to, let's see, it's going to be X1, Y2 minus X2, Y1. Okay, so it's kind of like a twisted dot product if you want. So in order to find X times Y times cosine theta, we had to take the dot product. And in order to find X times Y times sine theta, we have this twisted dot product. Okay, so this thing here, I'm going to call it in a second here. I'm going to call this X cross product Y. Probably I should use A and B for vectors instead of X and Y so we don't confuse what X is. But in a second, I'm going to call this the 2-dimensional cross product instead of dot product. It's like a twisted dot product, and it has this sort of idea of rotation kind of built into its definition. Okay. So what did we show? We proved this theorem that if X and Y are in R2, then the area of the parallelogram spanned by X and Y is exactly this number, absolute value of X1, Y2 minus X2, Y1. Okay, so this gives you the purple area here if you have any 2 vectors. And this motivates the following definition. So cross product. If A and B are 2-dimensional vectors, and let's say that A has coordinates A1, A2, and B has coordinates B1, B2, then the cross product of A and B is A cross B, and I'm going to define it to be A1, B2 minus A2, B1. Okay, so it exactly matches this. Okay, and I'm also going to define grad perp, just like we did. So if A is in R2, again with coordinates A1 and then A2, grad perp, sorry, not grad perp, the perp of a vector Just a second. The perp. Grad perp is something else. If A is in R2 and A has coordinates A1, A2, then A perp is the vector minus A2, A1. Okay? All right, so 2 dimensions, though, is relatively simple compared to 3 dimensions. Let's go and let's talk about 3 dimensions. We're going to try to define the same sort of object in 3 dimensions, a cross product. Now, in 2 dimensions, we saw that the cross product had something to do with rotations. So in 3 dimensions, though, rotations are much more complicated. In 2 dimensions, you only have sort of one axis of rotation, the z-axis. But in 3 dimensions, you have many different possible rotations. In fact, any vector in R3 gives you an axis of rotation. So there's sort of a 3-dimensional set of possible rotations. And so the cross product, it turns out, has to be a vector. So in dimension 3, we are going to define A cross B, but it is a vector, not a number. Okay, so that's the main difference in 3 dimensions. Let's talk for a second about the properties we want the cross product to have. Okay, so properties. The cross product has kind of a weird counterintuitive definition. I can tell you, here's how you compute the cross product. Now, this is the cross product. Now go and apply the formula. But I first want you to kind of understand the formula. And so this is going to require us to think a little more abstractly about what we want the cross product to look like. So let's go back and look again at what it was in dimension 2 at the previous slide. So in dimension 2, we see that this is the cross product. And one thing to notice is that it is not symmetric in A and B. If you do B cross A, then you actually switch places with these two things, which means that you have the same as A cross B, but there's a minus sign. Okay, so let's say that the first property that we want is that A cross B better be minus B cross A. Okay, so it's going to be anti-symmetric. Okay, now one thing that gives us the right to call it a product is that it has a kind of bilinearity. So the second property we want is that if we have SA1 plus TA2 cross B, that this better be SA1 cross B plus TA2 cross B. This should be true for all numbers S and T in R, and all vectors A1, A2, and B in R3. Okay, and this was true. The previous one was true for all A, B, and R3. Okay, so now I'm calling this thing bilinearity. Why am I calling it bilinearity? Well, because there's 2 slots and it's linear in both slots. I only asked that it be linear in the first slot, though. Why not the second slot? Well, you could get the linearity in the second slot by using the first property to switch places, then applying linearity in the first slot here, and then using property 1 again to switch back. So you only have to talk about, because this is anti-symmetric, we sort of know what happens in the second slot by what happens in the first slot, because I can just switch places and put a minus sign. So therefore, if I know that I have this linearity in the first slot, I'll also have it in the second slot. So I don't bother to write it because it makes my formula long. Okay. The third property that we want to have is that the length of A cross B, so now it's a vector, so I got to take the Euclidean length. It's not just a number. This better be the length of A times the length of B times the absolute value of sine theta, where theta is the angle between them. okay? And of course, this thing here is the area of the parallelogram. All right, so that's what I want to happen. Let me give you two more properties if I can fit it on the slide. Property 4, I'll start over here. Property 4 is that, so you see, let's go back again and think about the 2D case. In the 2D case, I did this rotation of x to make x perp, and I dotted that into y. So the rotation that I needed to make here was a rotation with respect to the, with the z direction. Z was the axis of rotation in some sense. And so the axis of rotation is sort of orthogonal to the plane that x and y sit in. So in 3D, if x and y span some other plane, I would need to kind of do the rotation with respect to a vector which is orthogonal to both x and y. And the direction of the cross product in 3D kind of encodes the axis of rotation. And that means that I need the cross product to be perpendicular to A and to B. Okay, so I want A cross B to be perpendicular to A and perpendicular to B. Okay, so that's one property that I want. And the last property is that I want the 3D cross product to kind of agree with the 2D cross product. So I want that if I kind of view two-dimensional Euclidean space as being embedded in three-dimensional Euclidean space through the xy plane, that the cross product I define agrees with what I had there. So what do I mean? I mean that if I have, or maybe I'll call these A instead of X. If I have A1, A2, 0, cross B1, B2, 0, that I get, okay, it has to be a vector, but it'll be a vector in the z direction, which has the same value as what I had before. So I get A1, B2 minus A2, B1. So I want this to be true. Okay. These are the properties that I want the cross product to have. And we're going to sort of derive what the cross product must be, given that we want these properties to be true. The main things I'm going to use actually are these two properties and this property. And that's going to kind of lead us into the right direction. Okay, so let's turn to the derivation. And in order to turn to the derivation, it's useful to use the sort of standard basis vectors. So I didn't really talk about this in the last lecture, but in 3 dimensions, we use these symbols, I, J, and K with hats to denote the 3 special basis vectors. We call these basis vectors because we can make any vector in R3 out of adding multiples of these together. So if you want to make the vector 3, 1, 2, then it's 3i plus j plus 2k. Okay, I just points in the x direction, j points in the y direction, and and k points in the z direction. Okay, so let's see. I'm going to think about what the cross product must be by thinking about what the cross product of pairs of these 3 vectors must do. So given property 5 on the previous slide, what we want to happen in 2D, you see that this tells us essentially what I and j must do. So I cross j better be k. And by the anti-symmetry property, this better be minus j cross I. So I cross j better be k, and j cross I better be minus k. Okay? And now we're going to just appeal to sort of symmetry and say that, well, all the coordinate directions should kind of behave in the same way. So we're going to go ahead and fill out what these must be. J cross k is I, and this is minus k cross, sorry, I think I said j cross k is I, which is minus k cross j. And finally, k cross I is j, and this is minus I cross k. Okay. The other thing that we learn in 2D is that, or we can learn by thinking about the fact that we want this formula to be true, is that if A and B point in the same direction, then the angle between them is 0, and sine of 0 is 0. So if A and B point in the same direction, their cross product should be 0. The cross product is kind of largest in magnitude when they're orthogonal, just like the dot product is 0 when they're orthogonal and is largest in magnitude when they're in the same direction. It's kind of the opposite of that. And this means that I cross I equals j cross j equals k cross k equals 0. Okay, but now if you allow that, what I've written here looks kind of natural. And I did make some arbitrary choices, like why did I choose j cross k to be I instead of k cross j? Well, that was an arbitrary choice. And that's because when we label the coordinates in R3, we also make arbitrary choices, like why do we have the z-axis not pointing down instead of up? Oh, there's really no reason. But if you did that, you would start changing the signs here, okay? Because if you switch the direction of the axis of rotation, then you change the direction of the rotation. Okay, but okay, so the way that you can remember this is sort of through this cyclic pattern. Okay, so you go in a cycle. So if the cycle is preserved, then you have a plus sign. So I, j, k, I, j, k, j, k, I, j, k, I, k, I, j, k, I, j. So if you're going around the circle in the right way, then you'll have a plus sign. If you're going around the circle in the wrong way, then you'll have a minus sign. So if you did j, I, k, it would be j, I, k. You're going backwards, so you have a minus sign. So that's how you can remember the signs. Okay, now I'm going to try to explain why, just from knowing this stuff here and the anti-symmetry and the bilinearity, I can completely define what the cross product must be. So let's see that. Now I'm going to say, okay, suppose all this is true. Let's try to compute A1, A2, A3 cross B1, B2, B3. Okay, and let's, just for fun, write this vector as A1I plus A2J plus A3K cross B1, B1I plus B2J plus B3K. Okay, fantastic. But now what I can do is I can use the fact that the cross product is bilinear. I can take this and I can split them off one at a time against this whole vector. And then I can split off these one at a time against each of these. So you basically just expand. And I'm going to do this kind of quickly because, so I'm going to do it in the following way. I'm going to look for all the things that this thing touches. It's going to hit this one, and this one. And when I hits I get 0. So I only have to worry about this against these two. Okay, so here we go. Let's look at the A1I contribution. So we get A1, B1, which is 0. So A1, B2. And then I get I cross J, which is K. And then I get A1, B3, I cross K, which is minus J. Okay, so that's all the contributions from this guy. Now I'm going to look at this guy, A2J. So I get plus A2B1, and then I have J cross I, and j cross I see from the above is minus k. And then I have a2, b3, and I have j cross k, which is a plus sign in the I direction. Okay, I have two more to go because I have to take this one against the first two. Okay, so I have plus a3, b1, and then I have k cross I, which is j. And then I have plus a3, b2, which is k cross j, which is minus I. Okay, so hopefully oops, just a second. So hopefully I did that calculation correctly. Let's come over here now and collect all the terms. Okay, so I'm going to collect the I, j, and k component of each one. So let's look at all the terms which have an I, plus all the terms which have a j, plus all the terms which have a k. Okay, so all the terms which have an I, I've got just this and this. So I see that I should have a2b3 minus a3b2. Now let's collect all the terms that have a j. I have a3b1 minus a1b3, and all the terms that have a k. a1b2 minus a2b1. Okay, and this I could write as one vector without the ijk notation, like this, comma, a3b1 minus a1b3, comma, a1b2 minus a2b1. All right, so this thing is the cross product of A and B. All right, so I'm going to go ahead and define this now. So a definition, if A and B are in R3 with A equal to A1, A2, A3, and B equal to B1, B2, B3, then the cross product of A and B is A cross B equals, all right, so now I'm going to copy what I just wrote, A2B3 minus A3B2, comma, A3B1 minus A1B3, comma, A1B2 minus A2B1. All right, so that is the definition. And you can see why, if you just learn this for the first time and someone just slaps the definition down, you may kind of wonder what's going on here. But basically, you derive it just because you wanted those properties those 5 properties that we discussed before to be correct. Now, before I get into checking those 5 properties, because I said I want those 5 properties to be true, and then I said, okay, the cross product must be this, but I have to go back now and check that I actually got each of those 5 properties. Before I do that, let me talk about how you compute A cross B. So there are various ways. The first way is to remember the formula. This is not the recommended way. I can't remember the formula, so you probably can't either. Let me give you a second way. And this involves computing determinants. Okay, so let's do it in 2 dimensions. If A and B are in R2, then A cross B is the determinant of A1, B1, A2, B2. So you can take the vectors and put them as columns. You can also put them as rows. Okay, And you remember all the determinant means is you multiply the diagonal and you subtract the off diagonal, which is exactly what the cross product was in 2 dimensions. Okay. Well, in 3 dimensions, you can do the same. If A and B are in R3, then what you do is you do A cross B equals, and you say that it's the determinant. Again, I can use columns or rows. This time I'll use rows. You put the unit vectors I, j, k in the first row. Okay. And then you put the coordinates of the 2 vectors here. And you find that this is exactly what the cross product is. You remember that to compute the 3D determinant, you take this entry, and then you kind of delete this, and then you take the determinant of what's left, and you multiply this entry by the determinant of this little 2x2 matrix. And then you subtract it from this entry, deleting its row and column, and you take the determinant of the remaining 2x2 matrix with these 4 entries. Plus, again, this entry, deleting its column and row, times the determinant of the remaining 2x2 matrix. Okay, so this is how you compute determinant if you're familiar with it. And it'll give you the cross product. You treat I, j, and k just like scalars in this calculation. You follow it around, and then you'll get I times something plus j times something plus k times something, and that'll give you the vector. Okay. The third way is matrix multiplication. Okay, so I can write A cross B as the product of a skew-symmetric 3x3 matrix. So I put zeros on the diagonal, and I put the numbers in here like this: minus A3, A2, A1. You can remember that each index of A here gets put in the place where it's neither the row nor the column. So this is the 1, 2 entry, so it's A3. This is the 3, 1 entry. Sorry, this is the 1, 2 entry. This is the 1, 3 entry, so it's A2. This is the 2, 3 entry, so it's A1. And then below the diagonal, you just make it sure that it's skew symmetric. So this is A3, this is minus A1, and this is, something's wrong. Sorry, there should be a minus here. Yeah, so this is the minus signs have to be together in this sort of off diagonal thing here. And then below, you just switch the signs and reflect it across the diagonal. All right, so you take this matrix, and then you take the vector b1, b2, b3, like that. And you do matrix multiplication of this 3x3 matrix and this 3x1 vector. And this will give you the curl, written as a column vector. Okay, so these are the ways that you can compute. These are sort of the ways that you can compute the cross product, and it's helpful to remember. Most people can compute it using this formula, I think. That's how I was taught to do it. And the way to see that this is how you compute it is, again, just look at the formula, compute this, and notice that they're the same. All right, let's move on now to checking the properties of this cross product that we defined. Okay. Let's see. So let me go back, I'll go back to the slide where we had the properties. Let's go back. So here were the properties that we wanted to check. So first of all, the anti-symmetric property is kind of obvious from definition. If you switch places with B and A, you see that you need to put a minus sign in every entry to make it what it was before. Okay. This linearity property is kind of obvious from the matrix multiplication version of the way to compute the cross product, or by just looking at the cross product itself, you see that it's linear in all the entries of A, as well as the entries of B. So it's kind of, these properties are kind of easy to check. I'm not going to do it because it's kind of immediate. Okay. This property 5 is also true by definition. If I just make A3 and B3 be 0, then you check that the first two entries are 0 and the last entry is the same. Okay, so I really want to focus now on checking properties 3 and properties 4. Okay, so why are these true? Why do I correctly compute the area of a parallelogram? Well, we know that if you let both A3 and B3 be 0, that you definitely do, because we already checked that this is true in 2D. But checking it for an arbitrary vector A and B in R3 is a different story. Okay, and I also want to check that I have this orthogonality, that the cross product is indeed perpendicular to both A and B, both of the things of the arguments in it. Okay. So first I'm going to check that I compute the area of a parallelogram, and this is kind of a magical calculation. So we're going to check that the length of A cross B is the length of A times the length of B times the absolute value of sine theta. All right? Where theta, again, is the angle between A and B. I'm not going to write it this time. All right, so I'm going to give you an outline of the proof, and there's going to be one equal sign that I'm not going to check in full detail, and I'm going to leave as an exercise for you. Okay, let's start. A cross B squared. This is what I'm going to compute. Okay, and it is A2B3 minus A3B2. I'm going to write it. The square of a vector, the square of the length of a vector is the sum of the squares of its entries. Because I'm squaring everything, I don't have to be too careful about the order and where the minus signs go. Okay. All right, so I've got this. Okay, so now what you actually have to do here is you have to expand the square so that you have a whole bunch of terms, like 12 terms or something. And then you're going to recollect those terms using some careful algebra. Okay, so let's just say dot, 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 dot. I'm not going to give the details until you get this. So again, this is kind of elementary algebra, which is why I'm pretty sure you can check it. Okay, so this dot, dot, dot is an exercise left to the reader. Or in this case, the viewer. Ha, ha, ha. Okay, so I feel comfortable leaving this as an exercise because I'm sure that each of you can expand this, and expand this, and write that on one sheet of paper. And then on a separate sheet of paper, you can expand all of this and expand this and collect all the terms. And then look at your two sheets of paper and notice that that the two expressions are the same. And therefore, this whole thing equals this whole thing. Okay, but it remains to be checked. This is kind of a proof by brute force. Okay, well, now let's look at what these things are. This thing here, the first expression, is just length of A squared times length of B squared. Right, that's all it is. And the second one is just A dot B squared, because this thing in here is A dot B. Okay, but you remember that A dot B is exactly length of A, length of B, cosine theta. So this is A squared, B squared, and this is minus, and then I have A squared, B squared, cosine squared theta. Okay, and now you may see the trig identity. So this is A squared, B squared. I can factor that out. I get 1 minus cosine squared theta. And this is sine squared theta. So I get length of A, length of B, absolute value of sine theta squared. Okay, so when I take the square of the cross product, there's a little bit of magical algebra that you have to do. You end up getting the square of this expression. Now, since both numbers inside the square are non-negative, I can take the square root of both sides and take off the square. And that is the proof of this. I'm done. Okay. All right, so the length of the cross product does indeed give us the area of the parallelogram spanned by A and B. Let's now try to see why A cross B is perpendicular to A. So I'm going to erase all of this that I just wrote, so I can write it on the same slide. Okay, so the next thing is that we're going to check that A cross B is perpendicular to A, and A cross B is perpendicular to B. Now, the first thing I want to say is that I only have to check one of these properties, maybe the first one, because by the anti-symmetry, I get the second one for free. Okay, so let's see why. Let's say that I've proved the first one, that A cross B dot A is 0. Well, then I can try to see what I can do here, but I just now put a minus sign, and I write this in the other order. And now you see I used the fact that this is against the first one, and now that's 0 as long as I've proven this. That's true for all A and B. So I only have to check the first one by the anti-symmetry. Okay. So I'm just going to check this. All right. So there's a couple ways that you can do it. And one is by brute force, kind of like what we just did. And I'm going to do that for you in a second. The other way, though, is to think about determinants. Okay, so you remember that given the way that we compute A cross B with determinants, you can check that this A cross B dot A is just the determinant of A1, A2. Instead of IJK, I put A because whatever the IJK end up being here, I'm going to dot it into A. And so I basically get this. Okay, so if you believe that the determinant calculation is the way to compute this, if you believed what I said, then if you dot it into A, the A components would hit the IJK, so I might as well just put them directly in here, like that. And now you see that this is the determinant of a 3x3 matrix with two rows that are the same. And that's 0 because I have rows that are not linearly independent. Okay, so now you may not like that. If you're not familiar with linear algebra, you may not like that proof. If you are familiar with linear algebra, you will like the proof. But let me now try to do the brute force calculation. Okay, so let's just do it by brute force. A cross B dot A. This is A1 times A2B3 minus A3B2 plus A2 times the Y component, the J component of the A cross B, which is A3B1 minus, I have to make sure I get the signs right, A1B3. And then the last component is A3 times A1B2 minus, A2B1. Okay? All right. Now, let's see what happens here. I'm going to show that there are 6 terms, and they cancel in 3 different pairs. So here I have an A1, A2, B3. An A1, A2, B3. Let's see if we can find another A1, A2, B3. Here I found it. Those 2 terms cancel, you see, because this multiplies by this and gives me A1, A2, B3. And this multiplies by this and gives me minus A1, A2, B3. So those terms cancel. Okay, let's find another pair. A1, A3, B2. Okay, so I have minus 1 here. A1, A3, B2. A3, A1, B2 is here, but it has a plus sign, so they magically cancel. You see, you do have to be careful with the signs if you want to check this kind of detail. All right, so finally I have two terms left, so they better cancel. Here I have A2, A3, B1, and here I have minus A2, A3, B1. So indeed, all these terms cancel in the pairs that I've drawn here, that I've underlined in color. And so I get 0 just by brute force. Okay. So we've checked all the properties now of our cross product. We have all 5 properties. Let's go back and make sure. Where were those properties? Okay. So we definitely have the anti-symmetry by the definition. We definitely have the bilinearity by the definition. If you don't understand why I'm saying that these two are obvious, then look at it for yourself and pause the video or whatever and think about it for 5 minutes, or take out a piece of note, like a notepad or a piece of scratch paper, and do the calculation for yourself. And when you find yourself doing the calculation, you'll be like, yeah, okay, it's not very hard. This one we checked, although I left the details to you in some sort of long algebraic calculation, and you should again check that on a notepad. This we just proved twice, and this again is true by definition. So we're happy with this definition of cross product. It has all the properties that we want. Okay. Let's talk about triple products. So the thing I want to tell you now is that if you have 3 vectors in R3, what you may want to know, if you haven't already asked yourself, because we sort of asked the question in 2 dimensions, what is the volume spanned by the sort of 3-dimensional version of the parallelogram, which is called a parallelopiped, if you can manage to pronounce it right. What is the volume of this parallelepiped spanned by the 3 vectors? Is there a way to compute it? And the answer is yes. It involves both the cross product and the dot product. In fact, what you do is you take the cross product of 2 of them. That gives you the volume, or sorry, the area, the 2-dimensional area of this parallelogram. And it gives you the orthogonal direction. That's what you get when you've computed this. And then you dot it into the 3rd vector, the dot product. You dot it into there. And that will give you the volume. So it turns out that, I'm going to try to explain this now. The volume of the this is a long word, parallelepiped, spanned by A, B, and C equals A cross B dot C equals A cross C dot B, and so on. You can, I should put absolute values here. You can take any pair you want, B cross C dot A, in whatever order you want, but you have to use all 3. Okay? This is a fact. Let me try to explain why this is quote unquote obvious from the properties of the cross product and the dot product. Okay. And I'm going to do that by sort of waving my hands at this picture. So first, let me erase the rest of this. Okay. So we know that the area of this parallelogram here, the area, equals the length of A cross B. Okay? And in order to get the volume, we should multiply that area by the height of this P, this vector P. Let me use a different color. Okay, so in order to get the volume of the parallelepiped, I should multiply the area by the height. Okay, so the volume of all this inside equals A cross B times the length of P. Okay, where P is this P is the projection of C onto A cross B. Okay, and this is true because A cross B is really perpendicular to B and perpendicular to A, so it's perpendicular to this two-dimensional parallelogram. Okay, it's pointing in the direction orthogonal. And so the height of the parallelepiped is exactly, you should measure it on the sort of in the direction of A cross B. Okay, and so if you take the projection of C onto A cross B, you'll get and you take the length, you'll get exactly the height. Okay, and so we want to compute A cross B, the length of A cross B times the length of P, but these point in the same direction. So this is just A cross B dotted into P. Now, again, like if you did B cross A instead of A cross B, then this would be pointing down or something. And so they would be pointing in opposite directions. So they're pointing in the same direction up to a sign. So you really have to put the absolute value on this triple product there. Okay. So now we've agreed that the volume is the absolute value of A cross B dot P. Okay. Now, how do I get C out of that? Well, let's try to get the C in there. Let's write this as P plus C minus P. And let me draw you a picture of where C minus P is in blue. This thing here in blue, if that shows up on the screen very well, is C minus P. And you see that C minus P is perpendicular to P and to A cross B, kind of by definition of projection. So this equal sign here is valid because the dot product of this and this is 0. So I can add 0 to my equation, it doesn't change it. And now we can take this thing and say this is equal to C. So I get A cross B dotted into C. Okay, so that's how you compute the volume of a parallelepiped. Okay, another way of seeing this, by the way, how can you quickly compute this? Well, you could compute this with a 3x3 determinant and then dot it into C. But another way to see that this is kind of nice is that this is just equal to the determinant of C1, C2, C3, A1, A2, A3, B1, B2, B3. So in other words, the determinant of a 3x3 matrix like this gives you the volume of the parallelepiped spanned by the rows. I could also write it in terms of columns. And I could also switch the order of the rows. So typically you wouldn't write it like this. You would put A and B as the first two rows and C as the third row because that doesn't change the determinant. Okay. So it's really, you just take the three vectors, you put them as the rows or columns in a matrix, and you compute the determinant of that matrix. Okay. And that is the reason why later in the course, when we do change of variables in integrals, if you're familiar with single variable calculus, you know that you can do a change of variables in the integrand, and you have to kind of change the dx, right? You have to change you have to make a local change for the fact that you're stretching space or compressing it or something. Well, in multiple dimensions, you do as well. And if you do a change of variables in many dimensions, we'll learn later in the course, you have determinants popping up, determinants of the so-called Jacobian map. And that really is for this reason. It's for the reason that when you do a change of variables in many dimensions, you can kind of stretch space and squish it in various directions. And you want to know, how does like a unit cube get deformed? And it'll get deformed into this parallelepiped. And you want to compute the change of volume that results in that. And you'll end up with these determinant formulas. So if you don't know what I'm talking about, just wait later in the course when we do the change of variables formula and the determinant pops up. And then I'll say, remember back to the second lecture, I told you so. All right. Let's talk about the equation of planes. So the cross product, the point I want to make here is that the cross product allows you to compute a single vector which is perpendicular to two given vectors. Okay, so let's talk about this. Let's say that we want to compute, or we want to find an equation of a plane in R3 containing 3 points, 3 given points. And let's say that our points are A, B, and C. Okay, so I give you 3 points in R3. Maybe here's a crude picture. I give you A, I give you B, and I give you C. And you kind of want to find the plane, not just the triangle between them, but you kind of want to, it's hard to draw, but you want to extend the plane indefinitely and find the equation of that plane. The plane containing 3 points. Just like a line, there's a unique line containing 2 points. There's a unique plane containing 3 points as long as the 3 points are not all in the same line or something like that. Okay, so how do we do it? Well, what you do if you want to find the equation of a plane is you want to find the normal direction to the plane. Okay, so a plane kind of has 2 different directions that you can go because it's a 2-dimensional thing. But in 3 dimensions, there's going to be a unique normal vector, which is to the plane. So you're going to have some in pointing out where this makes a right angle down to the plane. Okay, so you think of in kind of sticking out of the plane. So for example, if the plane is the XY plane, then a normal direction would be the Z direction. So K, in would be K. So in is a vector, which is the normal direction. So we need to find a normal in to the plane. And normal here just means perpendicular direction. Okay, so it's like when you have a line, you find the slope, but when you have a plane, you want to find the perpendicular direction. That specifies the plane better than giving 2 kind of directions on the plane. Okay, and then let's see. So let's say that I find the normal direction. How will I know if some other point, maybe this point here, y or something, how will I know if that point is on the plane or not? Well, what you do is you take y, you find some point that you know is on the plane, maybe b, and you draw the vector to y. Okay? And you look at y minus b. So that's, or you can look at b minus y, it doesn't matter. Okay, so I take this this vector. Okay? And then I dot it into n, and I better get 0. Okay? And the reason is that if I didn't get 0, so let me draw another picture down here. Let's say that my plane looked like this, just so that it's flat. And let's say that my y was not on the plane and it was up here. And I took some arbitrary point on the plane. I drew the vector to y. And I also am given some normal direction sticking out of the plane, which is perpendicular to the plane. Well, then when I do y dot n, I get precisely, up to a constant, I get the length of the projection of y onto n. And if you're on the plane, your projection onto the normal vector better be 0, which means that you're orthogonal. I mean, if you pick the orthogonal direction to the plane, then vectors between 2 points of the plane better be orthogonal to it by definition. So this is just the equation. This is how you write the equation of a plane. So typically you write it in coordinates like this. N1 y1 minus b1 plus n2 y2 minus b2 plus n3 y3 minus b3 equals 0. This is the equation of a plane. Okay, and remember that b is the given point on the plane, and n is the normal direction to the plane. Okay, so this is kind of the point slope formula, if you want, for the equation of a plane. All right, so this sort of begs the question, all right, that's great, but how do you compute the normal direction? How do you compute these coordinates? Like, how do you find a normal direction to the plane? Well, we just learned how to find a vector which is orthogonal to two given vectors, and that is the cross product. So let me clear this out, except for the picture, and talk about how to compute n. Now, of course, if you want to find the equation of a plane, it depends what information you're given. But in this case, if you're given 3 points, here's how you do it. So how to find n. Okay, so of course there's going to be one normal direction up to a multiplying by a scalar. So I'm just going to find you one n. If you find n by a different method, it may be like minus 17 times my n, but whatever. Okay, so what I'm going to do is I'm going to take two vectors that I know are on the plane. And I was given 3 points, so I can find two vectors. I can find this one, for example, or this one. Okay, I could also, I even have a third vector. I have this one, but that is going to give me redundant information. So I'm just going to look at two vectors. Let me call them x and y. So I'll call this one x and I'll call this one y. So x is going to be a minus c and y is going to be b minus c. But in any case, you first find two vectors on the plane. Find two vectors between pairs of points on the plane. And you call them x and y. Okay. Now, the vectors are not allowed to be in the same direction, right? If the vectors were in the same direction, it means that the 3 points you were given are actually collinear. They're all in the same line, and that's not enough to find a plane. So I need them to not be in the same direction. I need that theta, the angle between them, is not equal to 0. Okay, otherwise I'm going to be in trouble. And then all I do is I define n. Okay, so I'm in trouble here because I have x cross y. Okay, so I should have not used x, but okay, I just take the cross product between x and y. And this gives me some vector n, which is orthogonal to both x and y. And I know n is not 0 because the length of n is the length of x times the length of y times the absolute value of sine theta. And this cannot be 0 because the angle between them is not 0. So I found my normal direction. All right, and using that normal direction, I plug into the formula that I had before, and I've got my equation of a plane. Okay, so that's how you find the equation of a plane. All right, finally, let's talk about the distance of a point to a plane. Okay, so let's say that we're given a plane. A two-dimensional plane, call it P. And let's say that we're given a point A. Okay, and we want to find the distance from A to P. So we kind of, here, let me scooch my point A over a little bit. So you kind of want to find where it makes this right angle, and you want to compute this vector. Maybe I'll call it P. Yeah, I'll call it it's lowercase p. Okay, so it's the sort of vector going 90 degrees out of the plane to the point A. Another way to think about this distance is it's the minimum of the length of A minus B such that B is a point on the plane. Okay, so you look at like all points down here B, and you move B around each time computing the distance to A until you find the one that's closest to A, which of course will be at the bottom of this vector P, and P will just be the vector A minus B. Okay. Okay, so how do we do this? Well, what we do is we find the normal direction in to P. So we're going to assume that we know in, which is the normal direction to P. Let's also assume that the length of n is 1. If the length of n is not 1, like maybe we computed it from before and the length was square root of 17 or something, then we just divide by the length. That some point, say C, belongs to P. Okay. So then what we want to do, all right, so let's redraw the picture. We have some plane here. We have a normal direction sticking out of the plane. We have some other vector or some other point, A, here. And we have some other vector, maybe C. Okay. We form the vector from A to C, and we dot it into N. Okay, so the distance from A to P is just, you take A minus C and you dot it into N. Now, and this is it, and you take the absolute value because it could be negative and you want to not make it negative. Okay, so why is this correct? Well, this number here, A minus C dot N, will be the same no matter what C was. No matter what C was. Because as I move C around, I'm just adding to C basically vectors that are on the plane. And all of those dot into N to give 0. So I can move C around, and this dotted into N will be the same number all the time. So if I took C1 and I took some other C2, the difference between C1 and C2 dot N is 0. So as I move this around, this number can't change. And when the C is exactly the right number B so as to minimize this, then the direction of A minus that C and N will be the same, in which case this dot product will exactly give you this length. And therefore, I know that I can do it with any C because it doesn't matter the C that I pick. So the distance from A to P is exactly the absolute value of A minus C, where A is the point, C is any point on the plane, and N is the unit normal to the plane. Okay, and that's how you compute the distance of a point to a plane. All right, so that is basically what I wanted to cover in this lecture. In the next lecture, I may say some more words about determinants and linear algebra so that you can understand a little bit better some of the concepts I explained in this lecture. And then I'll move on to talk about cylindrical and spherical coordinates. All right.